Swayam Prabha. Digital India. Educated India.
I want to talk about some parameters that we
effects, what would be the effects coming into the play?
It basically effective viscosity. Say for example, if you have a lot of sediment, maybe like 5% volume fraction, going close to the bottom of a plate. Okay, now it's water plus particles. Are you going to use the viscosity of water, or how will it change? If you have heat transfer is important, people use nanofluids now to increase heat transfer. So nanofluids is changing the conductivity. Okay, so the suspension of the particles conductivity is not the same as the pure fluid. Same way, if you have a lot of particles suspended in a fluid, viscosity may not be the same as that water. So usually what happens is that viscosity can be written as a function of volume fraction occupied by the particles. Conductivity of the mixture can be written in terms of, and I will talk a little bit about the details. So right now I'm just talking about phenomena, not the mathematical details. We will talk about it, but at least for us to keep in mind that yes, when particles are there, typically you need to have a 1%, 2%, 5% or 10% volume fraction. Then some of these thermodynamic and transport properties do change, and you have to take that into account sometimes. Okay.
Yes, sir. So will it be taken highly dispersed flows? Thermodynamic effects will it be there, sir? Highly dispersed flows, for example, volume fraction 70%, 80%, or 50%.
A very high volume fraction?
Yeah, thermodynamic effects will it be there?
Well, that's a great question. It's a question of it is important, but is it important compared to the other four effects? Okay, that's the kind of question, because yes, viscosity may change, but then maybe the other effects are that may trump that. Maybe inertia effect, buoyancy effect, or slip effect, the drag, may be much more important than the change in viscosity. Okay, so modeling is not easy. It's just a question of which effect is important. I just want to bring to your attention that the fact that there are particles in there, you just can't use the viscosity of pure fluid anymore. That's the main message. Now, whether it's important or not will depend on a certain problem. Okay. So now we talked about length scales. Now let's talk about time scales. Okay, that's what I wanted to do. There's a lot of message here, but I'm going to send these slides for everybody. I will send that slide, so I'm not going to go over this. The main thing that I want to talk about here is, imagine that you shoot a particle. So on the left here, let's say you shoot a particle at velocity v0 in a stagnant fluid. I'm trying to talk about what is the time scale of a particle, how to think about a time scale of a particle. So here is stagnant fluid, and particle is shot at velocity v0. It's the time scale on which that velocity will go to 0, because the surrounding fluid is not moving, so drag will make it stop. Okay. The rest is a lot of details. Okay. So how do you analyze that? You take the equation mass times acceleration of the particle. Okay, so Newton's law is the sum of all the forces, and we will talk about that. Okay, so you put all of them and you solve it, and what happens is that the answer is you get the velocity of the particle is going to decrease following this kind of equation. So in other words, it's going to exponentially decay towards surrounding fluid velocity. So every particle, if its velocity is different from that of the surrounding fluid, it will change and approach the surrounding fluid's velocity, and the time scale on which it happens is called the particle time scale. That's a very, very important quantity, and I call it tau p. Tau p is the time scale on which a particle will adjust to the surrounding fluid, and this is the formula. Okay, so if for those who are familiar, it probably you know it. Otherwise, this is an important. So this is a very important quantity. So time scale, it goes as diameter square, and it's proportional to 1 plus 2 times rho. Rho is the density ratio. Rho, I will keep using that, is the particles density divided by the fluid density. And then in the denominator you have the kinematic viscosity of the fluid, and this phi is a very interesting parameter. So this is 1 if the particle is a low Reynolds number. Okay, so if the particle Reynolds number is very small, it becomes 1, and then the formula becomes dp square times 1 plus 2 rho divided by 36 nu. Okay, so that's a thing I tell my students that they need to remember that. Even when they wake them up, they should repeat that. It's a very important quantity, which is the time scale on which a particle adjusts to the surrounding flow. Now this is a very interesting thing, is because you can ask questions, what happens if the fluid in a turbulent flow, the surrounding fluid velocity keeps changing? I mean, you could ask a question, if the surrounding fluid changes on a time scale faster than this, the particle will never catch up with the flow. It's always, it tries to catch up with the flow and the fluid has changed. On the other hand, sometimes the particle is so small. So that depends on this diameter. So essentially what the lesson is, very small particles, micron sized particles, can move with the fluid without any problem because they adjust. Whereas if you throw a cricket ball in a turbulent flow, it will never, I use, by the way, baseball there, but here cricket ball is much more appropriate. So a cricket ball will never follow the fluid because its inertial time scale is too long. Okay, it responds only to your initial velocity, not to the fluid. Whereas a micron sized particle, you could have injected it at some velocity, but within a microsecond it has forgotten the fact that you have thrown it in the fluid. It will just follow the fluid. Okay, so those are very, that's why this quantity is a very important quantity. So here I was embellishing a little bit more. This formula that I have is sometimes different. You might find this to be different from many applications that you may see and think, because there are people who give time scale to be a little different for heavier than fluid particles, or when the Reynolds number is small, they may make some changes. But this is a very important quantity. Yes.
Sir, can you please go to the previous slide?
Yeah.
So in this slide, I think this tau p can be called as a time constant for the particle.
Yeah.
So,
So the beauty is that phi is the one that stops it being called a time constant, because the phi depends on Reynolds number. Okay, it depends on the nonlinear. Does the fluid follow the fluid or not? Does the particle follow the fluid or not? Depends on drag, and the drag depends on Reynolds number. So that makes it a little complicated. Okay, if the particle is very small, then tau p is a constant, phi is equal to 1, and we will talk a lot more about this.
so for single particle also that phi will.
This is for a single particle. This is everything I'm talking about, an isolated particle. Okay.
So effectively the time constant will be the time for the particle to attain the velocity, that is 63.4% around of the fluid.
Absolutely, it's to 1 over e it approaches. The difference decays to 1 over e. That's the technical detail. Okay. So if you wait for 3-4 time constants, it will virtually be. It's a time scale rather than precisely it will reach that. It's a time scale on which exponentially it approaches the surrounding fluid velocity. Now what about temperature? Okay, if a particle's temperature is different from that of the surrounding fluid, will it reach the same temperature? Well, tau t, this is the formula. So again d square comes, so very small particles essentially have the surrounding fluid temperature. Okay, whereas very big particles can be substantially different temperature. Now you can extend this to rotation rate. Does the particle rotate with the surrounding fluid? if the fluid has some vorticity, will the particle be rotating? Well, there is a rotational time scale, okay, and I didn't give that, but in the lecture notes in chapter 2 you will find time scale on which a particle will spin and spin as fast as the surrounding. Again, it's proportional to diameter square. Okay, always diameter square is the thing. The smaller the particle, faster it will adjust to the surrounding flow. Okay. The other interesting quantity is settling velocity. What is the velocity at which a particle settles? And that is given by this formula. Okay. So the key is a prefactor is rho is again density ratio. Rho is equal to rho particle divided by rho fluid, how heavy the particle is. Of course, when rho is 1, it is a neutrally buoyant particle, so it goes to 0. And when rho is 1000 times heavier, the numerator gets really large. And in fact, this ratio for a heavy particle becomes 1. Okay. For a bubble, it is the opposite, it becomes negative. In other words, bubble rises rather than sink. So you can, for bubble, rho is 0. Okay. So you have minus 1 divided by half. Okay. And tau p is what we saw earlier, times constant that we talked about, okay, and times g. So it's a very simple problem. A inertial particle, inertial means large tau p will settle fast because it's heavy. A light particle who responds to the fluid doesn't settle a whole lot. Okay, it's very slow to settle. So this quantity Vs is also proportional to diameter square, because tau p is proportional to diameter square, and therefore settling velocity is proportional to diameter square. Now another concept is Reynolds number based on settling velocity. Okay. And you can see its definition is very simple, diameter times relative velocity. Okay. But if you want settling based Reynolds number, here it is. Okay. It's the diameter times how fast is settling divided by viscosity of the fluid. Now I am not going to go into the gory details, just to give you some idea. In the lecture notes I calculated and I plotted them. So what's done here is size of the particle. So you have a millimeter sized here, this is millimeter, this is a micron sized particle, and much larger particles are to your right. And on the y axis is tau p in terms of seconds. Okay. And 3 different cases. What happens if you have a water droplet in air, or a sand particle in water, or air bubble in water? So 3 different cases. Water drop in air, density ratio is 1000. Sand particles in water, density ratio is 2.65. Typical sand particle is 2.6 times heavier than water. In air bubble, its density ratio is close to 0. Okay. So we see all these things, so you can get a rough idea. So I consult these pictures often because it gives you an idea about, hey, how fast it will adjust to the surrounding flow. And you see, the one interesting that you find is that they all sort of like, this is diameter square. So this is like slope 2, because the phi is 1 here, that the Reynolds number effect is not there. The Reynolds number effect. So all these particles, very small particle, Reynolds number is very small, Stokes drag works, and therefore you strictly follow diameter square. Now the important thing I want to say is that when particles get larger, it doesn't continue to increase as d squared. The drag increases further. So in other words, a bigger particle may catch up faster than what you would have expected based on Stokes drag. So the finite Reynolds number drag makes a big difference. Okay. So in other words, this becomes important even for a millimeter sized particle. A millimeter sized particle may be settling with Reynolds number say 10 and so on. So finite Reynolds number effect becomes important. So this is thermal time scale, and I want to skip that. So here is the settling velocity. So this is a question. So if you have an isolated particle of varying size, millimeter here and a micron here, And you have meters per second, the settling velocity, okay? And again, you see the same thing right around here. So 100 micron particles, Reynolds number is about 1. If you go higher than 100 micron sized particles, sort of simply falling down. Even if you have sand particles of 1 millimeter, it settles, its Reynolds number is bigger than 1. So that's something to keep in mind. So that's exactly what I said is plotted here. You can see this is Stokes flow, finite Reynolds number flow. So let me erase that. Okay. So you see that I have drawn a horizontal line at Reynolds number 0. So you can see all these particles settle at Reynolds number less than 1. These particles have finite Reynolds number effect. That changes the slope of these curves. Okay. So Stokes number is the concept that I was earlier talking about for spinning vortices, etc. So Stokes number we will talk very often. It's basically what I said earlier is the tau time scale of the particle versus fluid time scale. If Stokes number is less than 1, particle adjusts to the surrounding flow very fast. If Stokes number greater than 1, it's more like a sports ball being thrown in surrounding medium. It's not responding to the surrounding flow. It's more responding to what you initial kick you give. Okay. So you can see that very clearly in this sort of converging nozzle. The fluid velocity increases. Upstream the particle, if there was enough length, the particle is going at the same speed as the surrounding fluid. Say, let's say it has equilibrated. Now as the fluid is accelerating, will the particle accelerate? How fast? Okay. Now a lighter particle will just follow lockstep with the fluid because he is responding to ever accelerating fluid immediately. So the picture looks like this. So this is what you will see for the fluid does, the solid line is for the fluid, and the red curve I have drawn on top of it is what a micron sized particle will do very fast. 100 micron particle, maybe a millimeter, maybe a couple of millimeter. Whereas if you had a large, it may not respond at all. It may just continue to go ignore the fluid, maybe change a little bit. That's what is. So Stokes number less than 1 will follow the fluid, and out here you will have Stokes number greater than 1. So Stokes number is a very, very important quantity. Now the issue is, I said micron sized particle will adjust, but what if it's not a slow converging nozzle but a shock hitting the particle? Shock hitting the particle, a particle is there, a shock comes, there was no fluid motion, and suddenly as soon as the shock goes, the fluid velocity could be 300 meters per second. Boom! Fluid time scale is in nanoseconds or maybe shorter. So what I'm trying is that 1 micron particle is its Stokes number less than 1. It's not always less than 1. It depends on what you do. If you deal with, say, sort of environmental flows which are sort of slow moving, even 100 micron Stokes number may be less than 1. In the hypopicnal problem that I talked about, even up to even a millimeter you may say, oh, it's not that big, because the fluid motion is slow. Whereas if in engineering application, a fluidized bed or something like that, 10 micron may be small, but maybe 100 micron or 1 millimeter is too big. Whereas in a shock, even 1 micron is really too big. You really need to have molecular scale for it to respond rapidly. So Stokes number is an important quantity, and it changes from problem to problem. Now this is the interesting thing. So what about a vortex? Okay, the vortex time scale is omega is strain rate, so it has time scale of 1/2. Therefore, inverse of that is second. So what Stokes number is omega, the vorticity strength, times tau p. So if you have an intense vortex, omega is large, then even small particles will be spun out. But if you have a weak gyration, you really need big particles to be spun out. Same thing applies, just like earlier we saw, when density rho minus 1 is very important. Okay, this effect later we will see that density ratio, whether it's bigger than 1 or less than 1, is important. If the density ratio, if the fluid and the particle are the same, it won't be spun out or pulled in. Heavier particles, if rho is bigger than 1, it will be spun out, and if rho is less than 1, it will be sucked in. Okay, and that depends on Stokes number. So will a 1 micron or a 10 micron or a 100 micron will be particle heavier than fluid, will it be spun out? Depends on how strong is the vortex. Just the size itself is not good enough. It is size versus the time scale of the surrounding fluid.